Hi everyone. So we start the class. So today I want to do the lab session. So the examples of logistic regression, linear discriminant analysis, and the quadratic discriminant analysis, and also the nearest neighborhood methods. Then after that we do exercises. But I think that before that we haven't really finished everything in chapter 4. So we want to finish it first. So we will have some exercise time today. Do you have any questions so far for the previous quizzes and the lecture? Okay, so I will share the screen. Yep. Yep. So last time that we studied several methods, linear discriminant analysis and also QDA and the KNN. So also we have studied logistic regression last week. So the now that we want to see what's the difference, which model is better for, under what situation. Okay, so yeah, comparison. Yeah, so you want to compare these four methods. These four methods are all used for categorical data analysis. And the logistic regression is for only the binary classification. If we combine the several logistic regression or that we do multinomial logistic regression, that we can still do the multi-category analysis. And the LDA and the QDA are good for the multi-category analysis with more than 2 classes. And the nearest neighborhood is the more non-parametric method. So it's more data-oriented method, and it can be used for any categorization problem. So KNN is non-parametric, so we don't have much theory behind it. For example, the no testing is involved, and the no parameters are involved, so we cannot see any significance. But it's more flexible than other models. So it may be beneficial for more complicated data set. Yeah. And remember that the logistic regression and the LDA have both linear decision boundary, but the estimation methods are different. So logistic regression is based on logistic function. So we have some underlying assumption that the probability is represented by logistic curve. And LDA is based on maximum likelihood of Gaussian densities. So Gaussian densities, what's the distribution function? Basically, the Gaussian density is based on the distance between the center and that observation. So the likelihood is determined by the distance between the center and that observation. So more distance-based the method. So we have slightly different function, but anyway, the boundary is linear. LDA is a little more convenient in the sense that if we have more than 2 categories, that we can just separate the entire space into those categories. If we have the 3 categories, we can exactly separate those space into 3 categories. Logistic regression, more, the pairwise comparison. So sometimes if we have more than 2 categories and we apply pairwise logistic regression, we have trouble to decide a certain point. Which category the certain point belongs to. And in terms of the complexity, the KNN is most complicated because it's not based on a specific model, but more data-oriented method. Especially the KNN is based on the K nearest points from each point. So if K is small, then of course the rule is more complicated. So K is, for example, 1, then we consider just closest point to the so for any picked up any point for any point that we only choose just one point closest to that point. So it really flexible method. Even the boundary is really complicated. If the nearest point is obtained, then just we follow that observation to make the rule. KNN with large K is less complicated method, so the boundary becomes smoother. So if we take, for example, 100 nearest points of certain point, then that is just determined by the overall situation near that point. So it's not specific to that point, but we take the 100 points. So 100 points, the result is more stable. So the boundary becomes smoother than smaller k. And QDA is more parametric methods. So if the data size is large enough, then the less flexible, but the more robust estimation than KNN. And LDA is a simpler version of QDA. So in QDA, boundary is hyperbolic, but the LDA linear, so it's simpler. So that is LDA and LR, the logistic regression, are simpler. And forecasting performance, if boundary is simple, the simpler model is usually better, LDA or logistic regression, and KNN may be worst. But the complicated boundary, of course, LDA or QDA or logistic regression, they cannot formulate the boundary. So KNN should be the best. So several examples, model prediction performance by simulation. And based on the classification error rate. So if we see the boundary as a graph, then it may be easier to see, but there are less, objective results. So we want to calculate the error rate and compare that error rate here. We have several different simulations. So we have the 6 different scenarios. So scenario 1. So we use the Gaussian densities with no correlation between x1 and x2, and we, make the random points based on this rule. So that means that we prepare the 2 bivariate Gaussian distribution, and based on those distribution, we generate the points. So the truth is actually the LDA for this case. And the scenario 2, it's slightly more complicated, the Gaussian density with positive correlation between x1 and x2. So still the LDA's assumption that perfectly describes the relationship. And the scenario 3, the T densities with no correlation between x1 and x2. So, okay, so this is really similar to scenario 1, but densities are slightly different. So generally, Gaussian distribution has lighter tail than logistic regression. So remember that the Gaussian distribution, what's the distribution function? So exponential of negative x squared, that is the basically base of the Gaussian density. But logistic regression, actually the tail part is approximated by exponential of negative x or something. So maybe exponential of negative absolute value of x. So it has slightly heavier tail. So maybe it's similar, closer to T distribution. So basically more outliers in scenario 3. And the Gaussian distribution is light-tailed. So it's not robust against outliers, right? So if we think about the e to the power negative x squared, and x is very large value, then likelihood function is very small. The likelihood is very small for that point. So that means that point affects the probability a lot, right? So suppose that we fit the Gaussian distribution, and the Gaussian distribution is exponential of negative x squared, then one observation has x is equal to 100. Right? Then that density is really small. So basically that destroys everything. So even one outlier that destroys everything in Gaussian assumption. But logistic regression, that distribution is just exponential, maybe exponential of the negative absolute value of x. So if x is really large, such as 100, okay, still it negatively affects the likelihood, the entire likelihood, but it affects less compared to the Gaussian density. Okay. So likelihood estimation, we multiply likelihoods, right? So if one likelihood is very small, such as 0.000001, then that breaks everything. But the logistic regression, relatively, they're more stable. If we use the more heavy tails distribution, such as Cauchy distribution, then we have even more robust results. And scenario 4, the Gaussian densities with different correlation between x1 and x2. So last time we remembered that we studied that if we assume the two Gaussian distribution with different covariance matrix, then boundary becomes quadratic because the quadratic terms do not cancel when we do some algebra. So this is based on QDA assumption. So it should work well for QDA, but maybe LDA and logistic regression may not be enough. Scenario 5, the Gaussian density with no correlation for x1 square, x2 square, x1, x2. So we have more complicated pattern than just the usual LDA assumption, but it's limited to the quadratic term. So maybe QDA can deal with it relatively better than LDA. And scenario 6, it's not described. The algorithm is not described, but the very complicated rule so that the neither logistic regression, LDA, nor QDA can identify the structure. So probably K and N will work better. And scenario 1 and 2, okay, based on LDA assumption and which model is best. Basically, LDA and logistic regression works almost in the similar way, but the true distribution is exactly the LDA's assumption. So LDA performs marginally better than logistic regression. So this is error size. The y-axis is error size. And the QDA, okay, so still QDA includes all LDA cases, but we have redundant parameters, so it will add some noise. So it's slightly worse. And the KNN, much more flexible, but the flexibility doesn't help in this situation. So performance is much worse, especially KNN1. We overfit the situation. So even if the boundary is linear, just the KNN1 picks all of the exceptional cases as decision boundary, so it performs worse. Scenario 3, scenario 3 is similar, but based on T densities. So logistic regression probably works better than LDA, and actually in this simulation, logistic regression performs better. So even linear boundary, when we have many outliers, logistic regression may work better than LDA. And KNN and the QDA. QDA is also based on normal assumption, right? So it's similar to LDA for the non-robustness against outliers. So QDA performs worse. Actually, the true boundary is linear, so the LDA works better than QDA. QDA is even much worse than LDA. Especially, if the estimation doesn't work well, but we have too many parameters, we have a lot of trouble in estimation. So that's why QDA performs worse than LDA. And KNN, actually the KNN's performance is similar for here, here, and here. Okay. Not fantastic, but KNN with moderately large n. So this KNN CV is the K nearest neighborhood. In K nearest neighborhood, K is chosen as some optimal way. So it doesn't perform fantastic, but still it works reasonably well. KNN1 suffers from overfitting. Scenario 4 is based on the QDA assumption. So QDA works much better, and the LDA and the logistic regression perform much worse than before. And KNN CV, this is always, the somewhat good performance. So it's actually here better than these two methods. Scenario 5, we added extra terms, x1 square, x2 square, x1, x2. So more complicated boundary. So the KNN and LD at the QDA. QDA actually works best in this case. And the KNN, the CV, this performance almost similarly. And the KNN1, it's worse than this, but still it's better than the LDA and logistic. Of course, if true decision boundary is very complicated, the linear boundary models do not work well. Scenario 6, really complicated model. KNN CV is the best, then QDA next, and the LDA and logistic are not good. Yeah, so basically this tells that which model is the best. Which model is the best? That question depends on the data. So that based on the true data, the best method is different. So you can try these methods. Yeah. Also, I want to mention that, for example, this scenario, Gaussian density with no correlation for x1 square, x2 square, x1, x2. Probably we have a better way to deal with this situation. If we put these three terms in logistic regression or LDA, then we can separate this very well, because that is exactly the assumption. And that assumption is often true. For example, the real estate price is determined by the distance from the train station or city center. Then, the distance between 2 points is expressed by, the distance in x, the square of the distance in x-axis, and distance in y-axis, square of the distance between y-axis. So that means that is the quadratic, the equation, right? And if that is not just a simple distance, but we have some difference, such as if we have a slope, then even if the distance is small, still it takes more time to reach to the train station, then that also affects. So if we think about some maybe ellipse boundaries for real estate price, so then these three terms affect the real estate price. And actually in the past, one student did the logistic regression with these terms, and actually it works much better than the usual logistic regression. So just the point is that the LDA and logistic regression are really simple models, but if we add additional terms, sometimes it outperforms the QDA or KNN or even more advanced methods such as support vector machine. Okay, so this is always an option. In some case, we may add maybe cubic terms. Yeah, do you have any questions? Yeah, so these days the trend is always use deep learning or something, but sometimes the simpler model just works fine, especially with some additional transformed predictors. Okay, so next we discuss how to code logistic regression and LDA, QDA, and KNN in R. So you may find it you may find that these are actually somewhat simpler than linear regression, because linear regression, usually the more detailed diagnostics helps, but the classification problems that we don't have that much, diagnosis, and we don't have that much testing, maybe, and just more prediction oriented models. So maybe you may feel it's slightly simpler to analyze data. Okay, so you can see the chapter 4 lab slides available in Canvas. I will use the R console to explain that. So at first we have to, we have to load library. For data, ISWR package, ISLR package, sorry. And we use the stock market return data. Capital S market, that is the stock market data. So this is the daily stock market return for about 1,250 days from 2001 to 2005. So we use the S&P 500. And one interesting finding by economists is that the stock market return itself is unpredictable, but the direction of return is up or down. They can be predicted more than 50%, like 55, 60%. So that's a surprising fact. But that does not mean we can make money. So suppose that we expect tomorrow's stock market is up with 2/3 of probability, but we expect only 0.5% return. And we only have the 1/3 probability for loss, but the loss is expected to be -1%. Then that is just the fair deal. The expectation is 0. So even if we know that the stock market will be up the 2/3 of the time, but still we cannot make money. Okay, so we are doing that. And okay, so this is the today's return. So this is the return of the stock market on the first day of 2001. And these are just the 5 lags. So this is the daily return 1 day ago. And this is the daily return 2 days ago, and 3 days ago, 4 days ago, and 5 days ago. So if this is, for example, January 2nd, then this return is probably December maybe 30th, maybe when we skip the holidays and the Saturday and Sunday, Saturdays and Sundays, and here. And this is the stock return on maybe December 29th, and this is 28th and 27th or something like that. And this is the return for the next day, maybe January 3rd. Okay. Then this is the return 1 business day ago, so the January 1st. So that's why this number is the same as this number. And this is the stock return 2 days ago, so that is the same as this one, right? 2 days ago of the January 3rd, and the 1 day ago of the January 1st, January 2nd are the same. So basically these diagonal numbers are the same. And if the stock market follows some specific pattern, then the last 5 days move helps to understand the today's move. We have some additional information, volume, but I think we and we also use this as the predictor. I think this is not really the prediction in strict sense, because the volume is observed on the same day. So volume cannot be observed before the day ends. So maybe it's not entirely available. before the market starts on that day, but maybe, okay, so this is the experiment so that we try this. So we use these 6 variables as predictors to predict today's number. So this kind of strategy is useful for time series data. So to predict x sub t, maybe y sub t, we use maybe the log of y, log of t. So the y sub t minus 1, t minus 2, t minus 3, t minus 4, t minus 5, and maybe other variable x sub t. Yeah, but we are doing the binary classification, so we only consider the direction of today's return. So this is positive, positive, negative. So this is up, up, down. So direction is response here. And the predictors are log 1 to log 5 and the volume. And we use the GLM function, generalized linear model function. So this is the more general function than LM. LM is for linear model. And the GLM, direction log 1, log 2, log 3, log 4, log 5, plus volume, VOLUME. Okay, and yeah, so if we just type this, then R runs linear regression. But if we add additional terms, additional option, the family is equal to binomial, then we will fit the logistic regression. So family binomial. And the binomial option, the regression have several options, the logistic or probit or something. So you can see the help of GLM to see all possible options. And data is S market. Yeah, often some students that forget to write this family is equal to binomial. So in such a case, just this becomes LM model. Okay, so GLM. So maybe summary of GLM1. Then we can get this. Yeah, you can see that some outputs are different from linear regression, so you can see the difference. And also, yeah, you can see family binomial, so we can see the difference. So basically, we don't have F-test. We don't have F-test for logistic regression, and we have to use the theory of deviance. Maybe we covered a bit in Stat 5030 because that is more statistical class. But basically, we have to replace F-test by deviance test. So that's why we have this. And we have these estimates. And you can see this is Z value. So we don't have t-test for logistic regression. So we have the Z value. The meaning is similar, but still we have P value. So you can see that all the information are not significant. But for example, log 1, that we have a slightly small, relatively small P value. And that we have the relatively large coefficients. So log 1 negative. So if one day's return is positive, next day we will have negative return. We will likely to have negative return, maybe more than 50%. I think this kind of behavior is changing over time. If we use very old data, like 1980s or 90s data, then we have more negative correlation. Remember that we have the Black Monday in 1987. So we have 20% drop in one day in Dow index. And the next day we have a large jump. You know, information is less efficient at that time. So you work in a day, and after the day is over, that you see the stock market plummets in the evening news. Then they put some, order to buy stocks, and the next day, on the next day, the stock market will, skyrocket. So the information is, the less efficiently transmitted in old days, so more negative correlation between days. But now the correlation is really small, and I don't know, probably this one is much smaller. Maybe you can do in a final project, right? This is the data from 2001 to 2005. What if we use the most recent 5 years of data? Or what if we use much, the stocks with much lower volume, maybe international index or some specific stock, the very small stock, the maybe result may be different. Maybe that's an interesting project. Okay, so anyway, so these are the results. So log 1, log 2, negative coefficients, log 3 to 5, no, almost 0 coefficient, slightly negative, but if we see the standard error really small. Volume, we have positive coefficient, so larger volume, that means that we have larger gain. I don't know why. This is also not very strong, but still it may have some positive correlation. Yeah, so mostly we can only interpret the sign and significance of coefficients in logistic regression. It's really hard to see the direct implications such as slope. And okay, so forecasting is easy if this response is unbalanced. For example, if 90% of the days the stock market is up, then it's really easy to predict that direction. Always we can predict up, then we are 90% correct. Right? So we want to check what's the maybe we have to attach the S market data. Then we can summarize the direction, stock market direction in these 1,250 days. So stock market is down for the 602 days and up for 648 days. So it's almost the same, maybe 648, 1250. So if we always predict the stock market is up, then you are at 51.8% correct. So this is the baseline. We have to beat this number. So, and we want to see which is 1, which is 0 in this logistic regression. Then we can type the contrast of direction. Contrasts 0, 1. So the down is 0, up is 1. So we are predicting the up probability, the probability that the stock market is up. And we can calculate the fitted value of this model. For day 1, January 2nd in 2001, the stock market will be up with 50.7% probability. Day 2, maybe January 3rd, stock market is up with 48% probability. That is pretty low. That is pretty low. And maybe actually no significant days that the predicted up. If we see 30 days, maybe we have some good days, 29th day and 30th day, maybe like the February 10th or 15th. Yeah, so we have sometimes probability of 56% almost. So this is pretty high. Yeah, 48% isn't really good when the average is 51.8% up. Yeah, so some days are good and some days are bad. Is any of you invest in the stock market? Does any of you invest in the stock market? No.
A little bit.
Oh, okay. Do you have any strategy for the short term selling, buying?
Not really, no.
Not really, yeah. I think the one very useful factor is the VIX. This is the volatility index.
I'll have to check that out.
Yeah, this is very good to predict maybe, not really the short time, but like the 1 month or next 6 months return. The VIX is higher. That means the risk is higher. Volatility is higher. And risk is higher. We have a higher risk premium. So usually we have a larger return. So you are no free lunch, But if volatility index is large, then if you are good appetite to take risk, then you can invest it. So that's especially true in the stock market since last week, maybe up to yesterday. The Ukraine crisis boosted the VIX. Yeah, so no free lunch, but still we have some structure in the stock market. Yeah, so we can get the predicted value. Maybe we can decide the stock market will be up if probability is more than 50%. Yeah. You can also extract the coefficients. This may be useful to manipulate some numbers. I mean to do something more advanced by using these some numbers. It may be useful. Yeah. Yeah. So maybe we can replicate this fitted value by using these coefficients. We are using the logistic curve and the coefficients to estimate the probability. So the coefficients of the GLM, so these these numbers are just the same as these numbers, these estimates. So we can calculate the coefficient of the GLM1 and what time? Oh, okay. So the first one is intercept. So we multiply the intercept by 1. Then we multiply predictor values. So numeric S market of 7. So just first row. So the variable, so the predictors for the first observation. Okay. So we can multiply it. So we multiply this by the predictor variable. Then if we take summation, then we can calculate basically the B0 plus B1 x1 plus B2 x2 up to the BP xB. So this is B0 plus B1 x1 plus dot up to BP xB. Here P is the number of predictors. Then that is 0.02833. So if you use the logistic curve, that is the 1 over 1 plus the exponential of negative. Sorry. We have to name the output of the previous line. So this is the product of beta and x. So we name it as bx. Then we use the logistic curve. Then we get the fitted value of 0.507. So this is the same as this number by obtained by this fitted function. Okay. So in this way, we can calculate the fitted value of logistic regression. Yeah, and the GLM1 predicted so we use just the base rule. So if fitted value is more than 0.5, then we predict that the stock market will be up today. So GLM1 predicted. So we our prediction is here: the first day and the fourth day, fifth day, sixth day, and eighth day, ninth day, stock market will be up. So we can summarize this result and we can see if how many of them are correct. So direction is the true direction. So the rows that explains the predicted value. So predicted and the actual. And you can see that it's reasonably good, right? So yeah, maybe especially if we see this horizontally, when the predicted value is false, actually the more likely it's down. And predicted value is true, then more likely the stock market is up. So this prediction is probably better than nothing. Yeah, maybe we name this table as maybe the t.jlm1. Then we can see, the accuracy is this one divided by sum of tjlm1. Maybe you can even write the diagonal term of t.jlm. Then take summation, diagonal terms, summation of diagonal terms. So this is the correct percentage, so accuracy, the 52.2% approximately. So the stock market is up for 51.8% of days. So slightly it's better than this. So I don't know, this is not entirely the prediction. That we use just the entire training set to predict the training set. So it's not clear that if it will be the similar for test sets, but at least we beat the 51.8%. Yeah, so now that we want to evaluate test error, do you have any questions so far? So evaluate test error. This may be a little more difficult. So we split the data set into two. So training set 2001 to 2005. And the test set and 2005. So 2001 to 4 and 2005. So we have the column year. So year is less than 2005 that we define this as training. So we define the train as this logical vector. Value is 1 if 2001 to 2004. Yeah, and we define the test set as the S market 2005. So this as the stock market and the not training in training set. The exclamation mark is often the not in coding. So this is the test set. So now that we want to fit the model with training set and that we evaluate the performance by the test set. Yep. Yep. So GLM2, we define this as the GLM direction, almost the same as last time. Log 1, log 2, 3, 4, 5. And the volume. And we have already attached data, so probably we don't have to specify the yeah, but we have multiple data sets, so maybe just in case we specify S market. And So here, okay, so we want to only use the 2001 to 2005, the data for 2001 to 2005. So we specified the subset is equal to train. Train is the logical vector. So GLM2, so we have defined this and the summary of GLM2. So basically, this is the same as the last fit regression model, but we have slightly smaller data set. So we have slightly different result. Actually, this sign have been changed. And this also have been changed, even though anyway, it's not very significant. And first two, they're still negative, but the numbers have slightly changed. Similar, but slightly changed. Okay, then we wanna do test performance. So we wanna fit the model. Oh, sorry, we wanna predict the direction for the test set. And for the fitted value, the fitted probability, we have to type the type is equal to response. And we are using the data is equal to S market dot 2005. Maybe we have to say the new data or something, but actually we can omit this. I think probably new data. Maybe we can omit this for now. Then, okay, so GLM2 is just fitted probabilities. So now the GLM2, the predicted this as GLM2 fit, and this is more than 0.5. Then this is just the binary response, which is a 0 or 1. 0 is down, 1 is up. Then we see the prediction performance, the table GLM2 prediction S market dot 2005 direction. Then we can see this, yeah. So true and the false and up. So this 77 and these 44 are correct decisions. And 97 and 34, these are incorrect decisions. We predicted the stock market is up, but actually it's down. So it's errors. And stock market is predicted as down, but up. So these 97 are also errors. So we are correct in 77 plus 44 over the sum of these. So we are only 48% correct. But sometimes this can exceed much more than, 77 plus 44. Yeah, so we are only 48% correct. So it does not work anyway here. Yeah, so yeah, also we want to discuss the prediction for new data set. So basically the point is that when we want to do prediction such as this, the new data set should have exactly the same format as original training data set. In the original training data set, we have the columns of lag 1, lag 2, lag 3, volume, and response is what? Response is direction, right? So response, we don't use it, but we need the all predictors in exactly the same shape. So I think still it does not matter which row that it will be in, but at least we have the all predictors in that data set. So just to avoid any confusion, we detached the data set. When we attach, then we use the variable in the attached data frame as the default variables, but we have several data sets, so just in case we detach. And okay, so we define the log 1, 0, 0, 0.1, and -1. So we want to see the impact when the yesterday's stock market is just flat. And also we want to see the impact when the last day's return is very small negative value and also large positive value. And we also specify the log 2 to log 5. So first scenario is the log 1 to log 5 are all 0. And the second scenario is for these 5 days, the return is all the positive 0.1%. And the last scenario, the -1 5 days in the row. This is unlikely, but okay. So we have 5 days of negative return. Yep. Volume. Okay, so we can just ignore it and just we put some average value for 1.42. Then to get fitted value of this new data set, basically we have to make a data frame which has exactly the same shape. So data frame, we declare a data frame with these created variables. 3, 4, 5, and the volume. And we don't really need other variables such as year or direction. Just we need all predictors here. And just in case that we delete these ones, because we declared log 1, so this is just a global variable, but that's also in this data set. So this is confusing. So we just in case to avoid any confusion, that we delete these variables. So these variables still exist within this dnew, but the original the global vectors are eliminated. So these still remain locally in the dnew dataset. Then predict the GLM1 and the new data, dnew and type response. Then we get this. So 51%, 51.5%, 53.7%. So if stock market is down for 5 days by 1% each, really all investors become very pessimistic. But actually the probability that stock market will be up is much higher than other days. Maybe in the second scenario, the stock market goes up every day and the market is booming, so more people wants to buy stocks, but actually the probability is lowest among these 3 scenarios. Yeah, so these are logistic regression. Okay, so we don't really have much time, so maybe we stop the lecture here and I will give you some exercises. You can open the exercise 5 in Canvas, then you can discuss. And maybe I make breakup room, but breakout rooms, sorry. How many people here? 1, 2, 3, 4, 5, 6, 7, 8, 9 people. So maybe 3 groups, 4 groups, maybe 3 groups. You can discuss or you can just individually do it. It depends on the room. Move to 2. Okay. So you can do exercise 5. Okay, so hi everyone. Yeah, maybe I will ask the each of you which questions you have done. Maybe two more people, maybe. Okay, I think now it's done. Yeah, so it sounds that the A, everyone has finished, so that's good. And the B, maybe some of them, maybe 7 of you have finished. C, D, E, maybe a few of you did it. Okay, so maybe we wait. So A is what? A is the box plot. Yeah. So library ISWR package. This is another textbook. And malaria data. Malaria data is this. So that we have the subject age and the AB and the mal. Mal is the state malignancy, and the AB is what? The antibody, right? It's antibody. So we want to see the at first the age by malignancy. So we can maybe attach the data. Then after that, we can say the box plot and age over malignancy, and the maybe by label is age. Yeah, so we can see that. So actually the age one is malignant. So actually the lower age, the more malignancy, basically. Yeah. So malignant patients have lower the average age. Then next one. So what's the antibody? Antibody AB. Sorry, this is AB. But this is very skewed data, so we cannot really see the tendency. Actually the malignancy 0. That we have the higher malignancy and also make up a log of antibody by malignancy. So yeah, so the antibody level is higher for benign patient, but actually this is skewed graph, so we have many outliers here. So maybe the better representation is that we put the log of AB. Then we can see this, and we can clearly see the difference. So the antibody really determines the malignancy. But this is compared to the logistic regression, the analysis in the other way. So logistic regression explain malignancy by the response, the predictor variable. So here it looks like the malignancy is the predictor, and that we explain the log of antibody, but we do the other way around. So always when we analyze the binary response with the continuous predictor, we have two ways to analyze. We use response as the predictor response as the groups in T the comparison like t-tests or box plot. We can do it in this way, but also that we can analyze the malignancy by using the predictor of antibody. So at first, t-test. So we want to compare the malignant group and the benign group. And we can use the t-dot test function. Maybe we haven't covered in this class yet, but the t-tests probably you have learned in any statistics class, 20 to 10 or 20 to 10, 5800, and so on. And we pick up, okay, so t-tests for age, right? So t-tests for age. So age and the malignancy is equal to 0, and age for malignancy is equal to 1. So logical operation, you have to put 2 equal. So this means we determine whether the malignancy is equal to 1. Okay, so this is the group for malignancy, and this is the group for benign. Then you can see this. So actually, we have seen the difference, some difference in the graph, but also if we calculate the t-value and the p-value, okay, so we have some difference, but it's not significant at 0.1, I mean, the 10% level. Maybe you can do the same thing for log of antibody, log of AB, malignancy. Sorry, there's something is long. So log of antibody and the malignancy is equal to 1 and 0. Then you can see the significant difference between 2 groups. The malignant group has the average antibody level of 5.12, average log of antibody level of 5.12, and the benign group 5.12, and the malignant group the 3.74. So, and the difference is significant because the p-value is really small, and the t-value 4.6, so pretty large. So in this way, we can do t-test. And the question C already 6:45. So yeah, maybe we can do maybe C. You can do, this is pretty short, so maybe I can do it for a few minutes. glm.ag malignancy by age. So this is basically the analysis in a different direction compared to the t-test. Binomial logit. So actually, without specifying anything, then this becomes logistic regression. But also you can change this, the distribution. So you can use probit regression or some other models. Then you can do the summary of logistic regression, and you can see actually the age has negative effect. So the higher age, the less malignancy. And the p-value, okay, it's similar to t-test. T-test we have done, and the p-value is 0.0724. And here 0.0727. So it's similar. So methods are different. So of course it does not coincide, but actually the age is kind of marginally significant factor to determine malignancy. So the result is roughly consistent with the t-test. Yeah, this is the same just for log antibody. Yeah, so and E, F, G, yeah, you can see the, I will upload the solutions, so you will see. And another exercise that I will make it to the homework. So you can do LDA and QDA and the KNN for that homework. Okay, so that's it for today. So if you have questions, you can ask now. If you're not, see you on Thursday.
Thank you. Have a good night. Bye.
You too.
Thank you.